everyone, I'm Francesco Corsi from Hamlin Center and the Robot Intelligence Lab in Imperial College London. So minimally invasive robotic surgery instruments are introduced for small incisions on the patient's body, and this restricts the motion of the system, creating what's called the remote center of motion. So there are generally two approaches to solve this issue, which are design-based or control-based. In design-based, some mechanisms are properly designed to have this fulcrum motion effect. So a proper robot design is needed, and the RCM is generally at a specific location. Whereas in control-based approaches, an additional robotic arm is used. So the control algorithm is used to track the RCM, but this requires the kinematic models of both the surgical instrument and the serial link arm. So what we propose is to analyze how the mounting configuration between the surgical robot and a serial link arm in a macro-micro manipulator affects the system performance. And we propose a framework to identify the optimal mounting configuration for a given motion task. And also we propose a fitness function and a proper resilience to error strategy to guarantee that deviations from the optimum do not deteriorate the system performance in fulfilling the task. So in our approach, we have three main components, which are the optimization algorithm, the control strategy, and the resilience to error strategy. In this work, we are employing a KUKA 70OF KUKA arm, on top of which is attached our surgical robot, which is called the MicroGS. So in total, the system has 12 degrees of freedom. And for the MicroGS, since it is a tendon-dual robot, only the model values at the base can be measured and controlled. So given the kinematic model of the KUKA and the kinematic model of the MicroGS, it's then possible to combine the two models and get the full macro-micro manipulator kinematics, both at the post level and twist level. And what we want to optimize for is this mounting configuration matrix between the two robots. So for control purposes, we have a highly redundant system, so we can exploit prioritized optimal control techniques that allow exploiting redundancies, specifying different motion tasks, and avoiding conflicts between them. So we here use hierarchical quadratic programming, and we specify two tasks. The primary task is to track the RCM, and the secondary task is for tracking some paths, like for instance for tumor resection tasks. And it's then possible to easily compute, given a desired position of the RCM, to compute its kinematics, and so specify a desired velocity for the RCM. In our case, we are supposing that the tangential motion of the RCM, the RCM is fixed, so there should not be any tangential motion to the patient's body. For the optimization strategy, we employ a genetic algorithm, and this is because it doesn't require derivatives of the cost function. It finds the solution in a trial and error way, and also it allows having very large populations, and so effectively exploring large search spaces. So in our framework, the optimization variables are the roll picture in yaw angles that describe the rotation matrix between the surgical robot and the serial link arm, and our fitness function minimizes the tracking errors and maximizes the dexterity over the whole motion tasks. So it's made of two components, so the dexterity fitness and the tracking fitness. And then we propose this resilience to error strategy, and this is because small deviations from the optimal configuration may lead to much worse performance, yielding higher tracking errors and lower dexterities. So in our strategy, what we do is we first consider, for a given configuration, a neighboring region is considered. For each location in the region, we solve the motion task and we compute the tracking cost and dexterities, and we find the maximum deviation with respect to the values of the current configuration. And these maximum deviations are then used to penalize the fitness functions for the current configuration. So overall, our approach consists of 4 steps. So we start with a given configuration. We solve the motion task and compute dexterities and tracking costs. We evaluate the fitness function, and then we generate a new configuration, and then the process is repeated. Approaching simulation on three different motion tasks to generalize a bit better. And we first only optimize for the roll angle, and what we show is that with our fitness function, with our resilience to error strategy, we can find optimal solutions that reside in pretty stable regions, let's say. So where small deviations do not deteriorate much the dexterity or tracking errors. Then perform our roll pitch and yaw optimization, and we show that there are some configurations that lead to very poor performance in terms of tracking and also dexterity. And we can identify an optimal configuration instead. And this optimal configuration is again shown to be to reside within safe regions. So where there are small changes in the performance, if there's some small errors, with respect to the optimal configuration. Tested on the real robot. In this case, the whole system is required to cut only a single tumor, and we run the test 10 times. And we compare our optimized solution with the current mounting configuration. So these are the tracking tests on our system. So the system is required to follow a circular path, and we show the performance in terms of with and without the optimized mounting configuration. So what we show is that with our optimal solution, we managed to improve the system performance in terms of dexterity and accuracy, and to have a much larger fitness function. So this shows the improvement of the system's performance. We propose a framework to assess the capabilities of macro and micro manipulators depending on the mounting configuration between the two systems. Our framework allows identifying the best configuration that maximizes motion accuracy and precision and dexterity throughout the motion. And also our framework allows reducing the deterioration of the performances when deviating from optimal configuration thanks to our resilience to error strategy. However, our experimental results show some inaccuracies in the path tracking due to calibration modeling errors, and future work will focus on designing a reconfigurable connection between the two robots based on the optimal results from this proposed framework. Thank you for your attention.